On the 10th of April 2019, mankind saw a real image of a black hole for the first time. A black spot surrounded by a shining ring. Thanks to this photograph, we now have visible and direct proof of the existence of these mysterious and extreme objects. Even if it took many decades for physicists to be convinced, the existence of black holes is certain today. Black holes were a kind of mathematical curiosity, one of the possible solutions of Einstein's general relativity equations, but without real existence in the universe. In 1972, Steven Weinberg, future Nobel Prize winner, still qualified these objects as very hypothetical. The clues to their physical reality, however, accumulated. Among the latter, the LIGO and Virgo interferometers have detected gravitational waves, vibrations of space-time corresponding exactly to what is produced when black holes merge together. At the center of most galaxies is one of the most amazing things in the universe: a black hole. When a giant star loses energy, it implodes and collapses under its own weight, causing an explosion called a supernova. Reduced in the form of an infinitely dense ball, the star then turns into a black hole. Under the effect of the black hole's gravity, everything that approaches it is attracted, whether asteroids or giant stars. Nothing is fast enough to escape its pull, not even the light. Every object in the universe has what is called a Schwarzschild radius. If this object is compressed until it reaches this radius, calculated from its mass, a black hole is created. For example, the Schwarzschild radius of the Sun is 3 kilometers. It would therefore have to be compressed below this radius so that it gives rise to a black hole. In the case of the Earth, it would have to be compressed to the size of a ball with a radius of 0.9 centimeters to create a black hole. A black hole is extremely dense, with an intense gravitational field. It is composed of the event horizon, or the limit that surrounds it, from which the fate of the attracted entities is sealed. Nothing, not even light, the fastest entity in our universe, can escape from it, as the gravitational force is too intense. From this point of no return, the laws of physics no longer apply. Time is stopped, space is null, and the temperature is infinite. As an example, near quasar 3C 273 has a temperature of 10,000 billion degrees. Quasar are active galactic cores, made up of a supermassive black hole, around which enormous amounts of matter spin. Around the black hole are the accretion disks, composed of gas and dust of matter that undergo attraction, forming the representation of vortex that we usually attribute to the black hole itself. Nevertheless, these accretion disks are not specific to black holes, since they can also be observed around white dwarfs and neutron stars, for example. At the center of a black hole is the singularity, the point where all the matter of the celestial object is concentrated. Any object crossing the event horizon ends up falling in the singularity. There are different types of black holes, of any mass and size. The largest are the supermassive ones, with a known mass up to 40 billion solar masses and an area of tens of billions of kilometers. The largest galaxies have a supermassive black hole at its center, such as the black hole of the Milky Way galaxy, the Sagittarius A black hole. However, the gravitational force of supermassive black holes is not strong enough to absorb an entire galaxy. The more modest black holes are the intermediate mass black hole, and then the stellar ones, which are formed by the collapse of a massive star. Although this type of black hole extends only a few kilometers, its mass is still several times higher than that of the Sun. Moreover, if the Sun were to die, it would not become a black hole, but rather a white dwarf, since its mass is not large enough. Finally, there would exist microscopic black holes called primordial black holes, which would have formed at the time of the Big Bang. According to Stephen Hawking, their mass would be as low as 10 to the minus 5 grams. According to some physicists, these primordial black holes could correspond to dark matter. On the 14th of September 2015, LIGO interferometers located in the United States, intended to detect gravitational waves, witnessed an astonishing fluctuation. Once this fluctuation was made audible, the Laser Interferometer Gravitational Wave Observatory LIGO published 5 months after the results, according to which this noise came from the echo of the collision of two black holes located 1.3 billion light-years away, and of a mass equivalent to 30 suns. This was the first evidence of the real existence of black holes. Imagine throwing a book into the fire. It will of course burn, and we will no longer be able to read it. However, if you arrived at the moment when it is still possible to determine the position of the atoms, it would be possible to know the trajectory of these atoms, their starting point, and therefore to reconstitute the information contained in the book thanks to the laws of physics. Even if this remains theoretical, we have a property of microscopic physics here. If the state of a system at the present time is known, it is possible to determine its past state. Therefore, the information is retained, not deleted. Here lies the paradox. This property does not apply to black holes. Indeed, according to the Hawking radiation, established by Stephen Hawking in 1975, black holes evaporate over time, very slowly, but eventually disappear after an infinitely long time. However, according to the law of micro-reversibility of quantum mechanics, all information, even if it is transformed, cannot disappear. So what happens to the information captured by the black hole when the black hole completely disappears? As mentioned earlier, according to Hawking's radiation, black holes evaporate over time. Indeed, quantum physics implies that the vacuum is in fact the seat of a formidable activity. Particle-antiparticle pairs appear spontaneously and are annihilated very quickly. This temporary violation of energy conservation is permitted by the Heisenberg uncertainty principle. However, in 1975, Stephen Hawking noticed that if a pair is created just above its event horizon, one of the particles falls into the black hole while the other escapes. They can no longer be annihilated. To a distant observer, the black hole thus appears to emit radiation, Hawking's radiation. The black hole therefore loses mass. It evaporates. What if our universe was inside a black hole? Recent observations of the movement of particles absorbed by a black hole suggest that a black hole is not a singularity, as Einstein believed with his theory of general relativity, but a bridge to another universe. According to this theory, instead of reaching infinite density as they pass through a black hole, the particles would bounce and expand again. This theory would make it possible, in particular, to explain the direction in our universe of space-time, and many other still obscure observations, by relying in particular on the theory of Einstein-Cartan. Thus, the black hole would be a kind of passage from an old universe, the mother universe, to a new universe, therefore expanding, the daughter universe. This could totally impact our approach to the Big Bang, or rather the Big Bounce, as physicists call it in favor of this theory. According to the Big Bounce, our universe is the result of the collapse of another universe through a black hole. Another corollary of this approach is that there would be an infinity of universes, all accessible through black holes. What happens if a black hole meets Earth? To begin with, as it approached our planet, the black hole would first encounter the Oort cloud, a sphere made up of frozen comets, which surrounds the solar system at a great distance. The meeting of the black hole and the Oort cloud would project the majority of these comets towards the planets of the solar system, including the Earth. Once it reached Saturn, it would become visible from our planet. As the planets are absorbed into the black hole, an accretion disk forms around it, made up of burning gas and dust. Once at the asteroid belt, asteroids would also be projected towards our planet. Earth's atmosphere would then be torn apart by the black hole. Then the entire planet, piece by piece, our planet would then undergo the phenomenon of spaghettification, that is to say, it would stretch like spaghetti when it is caught in the gravitational field of the black hole. However, the black hole itself would not be impacted by this collision with Earth, since the size of the event horizon would only increase by 5.825 multiplied by 10 to the minus 5%. In the case of a black hole of a mass equivalent to 5 Sun, the collision would then release an energy equal to 8 nonillion, 945 octillion, 890 for septillion, 480 for sextillion, 833 quintillion, 720 for quadrillion, 900 to trillion, 386 billion megawatt hours. But don't worry, there is only 1 in a trillion chance for the Earth to collide with a black hole. But how did supermassive black holes form in the early days of our universe? Indeed, scientists observed that supermassive black holes already existed, only a few 100 million years after the creation of the universe. Yet, how to explain their formation? Since at that time, the first stars were not big and massive enough to form a black hole. There are currently two possible answers to this question. According to the first answer, it could be due to the possible collapse of sufficiently massive gas and dust clouds. According to the second answer, primitive supermassive black holes could originate from dark matter, one of the greatest mysteries in modern astrophysics. Although it's currently impossible to determine with certainty the composition of dark matter, its existence is known from the gravitational force it exerts on its surroundings. Dark matter is invisible to us because it is insensitive to electromagnetic force and does not absorb, reflect, or emit light. Dark matter constitutes about 27% of the universe, while the ordinary matter we know, which forms all stars and galaxies, constitutes only 5% of the universe's content, with the rest being dark energy associated with the vacuum of space. Primitive supermassive black holes could therefore originate from dark matter, considering that potential cores of galaxies made up of dark matter could become so concentrated that they would collapse into supermassive black holes. This would then explain the formation of the first supermassive black holes without requiring the prior formation of massive stars. A white hole, or white fountain, would be a theoretical celestial object symmetrical with respect to time to a black hole. Indeed, if nothing can escape from a black hole, nothing could penetrate a white hole. This celestial object is only theoretical, since its existence only comes from a thorough reasoning of the Soviet cosmologist Igor D. Novikov, starting from the relativity equation of Einstein in 1964. Mathematically, the most common solution to the equation of general relativity is the Schwarzschild black hole, characterized as eternal and static. Black holes have an event horizon that indicates the zone of no return for any object entering it. Nevertheless, by reversing the time variable while solving the equation, there would also exist inverse trajectories, which means there would exist forms of event horizon for a Schwarzschild black hole. It means there would exist several types of white holes, depending on the type of black hole concerned. A future horizon would describe a black hole as the region from which it is impossible to escape, and a past horizon would correspond to a region where it is only possible to exit. This region would correspond to a white hole. In the case of an electrically charged black hole, there could exist a black hole-white hole configuration, called a wormhole, where the white hole would be the exit of a black hole existing in another universe. The problem with confirming this theory and using it for interstellar travel is that it is impossible to get into a white hole. So all these properties are unpredictable. Many doubts remain on the existence of white holes since their creations are undemonstrable. We know that a black hole is formed by the contraction of the heart of a massive star, but to exist, a white hole should be present since the creation of the universe, or be the result of an unknown physical process. Hence, is the existence of white holes conceivable? The theory that could explain its creation, according to some astronomers, is that white holes would appear in the heart of quasars. Quasars are seats of physical phenomena still unsuspected in view of the power of its light rays visible from the Earth, despite the few billion light-years separating them. Unfortunately, the followers of this theory are very few since the properties of quasars would be explicable by the presence of a supermassive black hole surrounded by an accretion disk. Thus, one can still wonder if white holes will remain a false fantastic theory or a celestial object to be understood and demonstrated. The most surprising properties are those concerning the distortion of time around a black hole, as time flows more slowly in a strong gravitational field. It is in the extreme case of a black hole that this kind of effect is particularly spectacular. Imagine watching a friend in the distance diving into a black hole. As he approaches the singularity, you will see his watch turn slower and slower. The movement of the hand corresponding to 1 second will take more and more time. This second will become 1 minute, 1 hour, 1 day, 1 month. By the time he reaches the Schwarzschild radius, this movement will take an infinite time. The image of your friend will remain frozen for eternity. But if we take this situation in your friend's shoes, the situation will be reversed. When he reads the time on his watch, he will not notice anything special. But when he looks at yours, he will be astonished. He will see the hand turning faster and faster. A turn will be completed in a second, a millisecond, a microsecond. He will soon observe the life of the stars unfold in a fraction of a second, and then, by finally reaching the Schwarzschild radius, he will be able to observe the entire future history of the universe.